Chapter 18 DC Circuits.
This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out important updates from us.
There are two types of electrical circuits: series circuits and parallel circuits. For series circuits, the current at any point of the circuit is the same. The direction of the flow of the current is the same. This diagram shows a series circuit. We can see that all these current I1, I2, I3, they are the same, or in general, just an I. When two or more cells are connected in series, the total electromotive force EMF is the sum of the EMF of each cell. The terminals of the cells should be in the same direction. So for this diagram, these two cells are connected in the same direction. So let's say the first cell, the EMF is 2.8 volts, and the second cell, the EMF is 4.2 volts. So the EMF of point A to point B is the sum of these two cells, 2.8 plus 4.2, which give you 7 volts. Now, this second diagram shows that the first and the second cells, they are connected with the terminal in the same direction, but the third cell, the terminal is connected in the opposite direction. Let's say the first EMF is 2.8, the second EMF is 4.2 volts, and the third EMF is 1.4 volts. Hence, the EMF of point A to point B is 2.8 plus 4.2 minus 1.4, which gives you 5.6 volts. The total EMF of a series circuit is equal to the total potential difference in the circuit. The total resistance, RT, of two or more resistors arranged in series is the sum of the resistance of each resistor. So this diagram shows that the cells are connected in series, hence the total EMF is EMF1 plus EMF2 plus EMF3. Similarly, the resistors here are connected in series with R1, R2, and R3. So the current flowing through these three resistors is I1, I2, and I3. Since they are connected in series, all these current are having the same amount. Therefore, I1 equals I2 equals I3, which is also the I. When we measure the potential difference between these three resistors, the sum of the potential difference V1, V2, and V3 is equal to the total EMF. Therefore, we know that from Ohm's law, V equals to IR. So V1 is I1, R1, V2 is I2, R2, and V3 is I3, R3. Since the currents are the same, hence it becomes IR1 plus IR2 plus IR3. Then we can factorize the current becomes I bracket R1 plus R2 plus R3. Therefore, R1 plus R2 plus R3 equals to total EMF over I. Therefore, R total will be R1 plus R2 plus R3. In general, the total resistance equal R1 plus R2 plus to the last resistance Rn. N is the number of resistors connected in series. The second type of circuit is parallel circuits. In a parallel circuit, the current entering a node that splits into branches is equal to the sum of the currents flowing in each of the branches of the circuit. Similarly, the sum of the currents flowing out from each of the branches is equal to the current flowing out from a node. So this is the I, and this point is the node. It is split into branch 1, branch 2, and until branch n. So each branch has a current flowing. Let's say the first branch is I1, the second branch is I2, up to the branch n is In. Similarly, we can see that this branch 1, branch 2 until branch n, the current flowing out for branch 1 is I1, for branch 2 is I2, and branch n is In. These current flow into a node, and one current flowing out from this node is I. From here, the I equals to I1 plus I2 plus till the last current In. If two or more identical cells are arranged in parallel and their terminals are in the same direction, the total EMF of the current is equal to the EMF of each cell. So this diagram illustrates two cells are connected in parallel. So if both cells have an EMF of 3.0 volts, if we connect one voltmeter parallel to this cell, the voltmeter reading will give us 3.0 volts. Similarly, if we connect a voltmeter parallel to the load or the resistor, the voltmeter reading will give us 3.0 volts as well. If two or more identical components are arranged in parallel, the total potential difference PD of the circuit is equal to the potential difference across each component. So this diagram shows three resistors connected in parallel. So we connect one voltmeter parallel to the first resistor, second voltmeter connected parallel to the second resistor, and the third voltmeter connected parallel to the third resistor. So we will get all the readings of the voltmeters V1, V2, and V3 are equal. And the values should be same as the EMF of the cell. Let's say I is the current flowing out from the cell, and it is split into I1, I2, and I3. So from here, I equals I1 plus I2 plus I3. And I is EMF over R total. I1 is V1 over R1. I2 is V2 over R2, and I3 is V3 over R3. And since the voltage or the potential difference are having the same value, therefore 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. In more generic form, 1 over R total equals to 1 over R1 plus 1 over R2 plus till the last resistor 1 over Rn. So this is the formula to find the total resistance in a parallel circuit. simplifying series and parallel circuits. In series circuit, this diagram shows two resistors R1 and R2 connected in series. And there is one current I flowing through these two resistors. So each resistor has its potential difference. The first one is V1, the second resistor is V2. Hence, the total potential difference is Vt. We can simplify this circuit into one resistor with the value of R total and the current I, potential difference Vt. The total resistance is R1 plus R2. The total voltage or total potential difference is V1 plus V2. In a parallel circuit, we assume that there are n resistors connected in parallel. Each resistor has a current flowing in. So, for example, the first resistor, the current is I1, second resistor, I2, and the nth resistor is IN. The potential difference for each resistors are the same, which is Vt. We can simplify this circuit into one resistor with the value of Rt and the current I, the potential difference Vt. So the value Rt can be calculated with this formula: 1 over Rt equals 1 over R1 plus 1 over R2 plus, to the last resistor, 1 over Rn. Now, let's look at this example. Referring to the diagram below, find the value of I. The values of the resistance are shown in the diagram, and this is the I. You can pause the video and try to get the answer yourself. Now, let's look at the solution. Firstly, we need to know the equivalent resistance for the parallel resistor. We can use this formula: 1 over R T equals 1 over R1 plus 1 over R2. So the answer will be 1 over 20 plus 1 over 30, and we get the total resistance for this parallel is 12 ohms. Then we can change this circuit into the simpler form, where the 40 ohms resistor is connected in series with the 12 ohm resistor. So the total resistance will be 40 plus 12, which will give you 52 ohms. Hence, applying this formula, I equals to EMF over RT, which is 12 over 52, and the answer is 3 over 13 amps. Do you get the answer correctly? Potential divider. Potential divider consists of two resistors connected in series, which is used to produce variable output voltage. So this diagram shows a potential divider. We have the EMF at the cells, which also equals input voltage. So this is the current flowing in the circuit, the first resistor R1 and the second resistor R2. We can measure the potential difference of R1 and the potential difference of R2. So the current flowing into R1 is I1, the current flowing into R2 is I2. So since they are connected in series, the current is the same. I equals to I1 I equals to I2 as well. Therefore, V in over total resistance R1 plus R2 equals V1 over R1 equals V2 over R2. We look at the first part. V in over R1 plus R2 equals V1 over R1. Therefore, the potential difference in the first resistor Vi V1 equals R1 over R1 plus R2 times V in. Similarly, for the second resistor, V in over R1 plus R2 equals V2 over R2. Therefore, the potential difference for the second resistor, V2, equals R2 over R1 plus R2 times V in. So this is the formula for potential divider. Assuming that R1 and V in are constant, where R2 increases, V2 increases as well. We usually connect a load at V2. A potentiometer or rheostat is a variable potential divider. So this diagram shows a rheostat with its important parts are labeled. There are three terminals in a rheostat, which are terminal A, terminal B, terminal C, a sliding contact, and a coil of wire. So we can connect a rheostat series with battery. So this is the sliding contact. Terminal A is connected at this point. Terminal B is at this point. Terminal C is at this point. So the sliding contact can be slided from A to C. So when it slides, the resistance between A and B and C will change. Therefore, we'll get the output voltage equals length of BC over length of AC times VE. Thermistor is a type of resistor which its resistance changes with temperature. The resistance of a common thermistor decreases when temperature increases. The light-dependent resistor, or LDR, is a type of resistor where its resistance changes with the intensity of light shown on it. The resistance of LDR decreases as the intensity of light shown on it increases. Thermistors and LDRs can be used in potential divider circuits to control potential differences based on the surrounding temperature, for example, air conditioner and heater, and brightness, for example, automatic lamps. So this is the symbol for thermistor, and this is the symbol for the light-dependent resistor LDR. So now let's look at this diagram. We connect the thermistor at the first resistor. Recall the potential divider formula. V2 equals R2 over R1 plus R2 times V in. Also, the resistance of a common thermistor decreases when the temperature increases. Hence, when the temperature increases, R1 decreases. So the total resistance R1 plus R2 decreases. Therefore, V2 increases and V1 decreases. This circuit is a temperature control circuit. If it is used in a cooling system, examples are refrigerators and air conditioners, cooling fan is connected parallel with R2. The cooling fan will turn faster when temperature is high and turn slower when temperature is low. If it is used in heating system, example, water heater, heating element is connected parallel with the thermistor. The heating element produces more heat when the temperature is low and less heat when the temperature is high. Now, let's look at this diagram. This is a potential divider with LDR connected as R2. Recall potential divider formula. V2 equals R2 over R1 plus R2 times V in. Also, the resistance of a LDR decreases when the intensity of light increases. Hence, when intensity of light increases, R2 decreases. This causes R2 over R1 plus R2 to decrease. Therefore, V2 decreases. This circuit is a light controlling circuit. Automatic lamp is its common application. When a light bulb is connected in parallel with the LDR, it will shine brightly when the intensity of light is low. The light bulb will dim when the intensity of light is high. The light bulbs at roadside turns off automatically on daytime and turn on at nighttime.
That's all for this video. Thanks for watching. Do you have any question or doubts to ask? Feel free to write down in the comments. I would love to hear from you. Do you like this video? Please don't forget to like it and share it. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.